Tonight, we're going down the most profound rabbit hole in the universe, a place where the laws of physics, as we understand them, break down completely, where space and time swap roles, where every direction you can possibly move leads to the same inescapable destination. We're going inside a black hole, and by the end of tonight, you're going to understand why a black hole isn't just a hole in space, but something far stranger and more terrifying than that. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. You've probably heard the basic description. A black hole is a region of space where gravity is so strong that nothing can escape. Not even light. That's why it's black. Light goes in, light doesn't come out, so it appears as a dark void against the background of space. Simple enough, right? But that description barely scratches the surface. It doesn't capture the sheer weirdness of what a black hole actually is, or what happens when you fall into one. Because a black hole isn't just a very strong gravitational field. It's a rupture in the fabric of space-time itself. A place where the normal rules about past and future, cause and effect, even about what we mean by location, break down completely. Let's start with what we can observe from the outside, because that's the only perspective most of us will ever have. When you look at a black hole from a distance, you see nothing. Literally. The black hole itself emits no light, so it's invisible. What we can see is the effect it has on surrounding material. If there's gas or dust nearby, that material falls toward the black hole, and as it falls, it speeds up and heats up through friction and compression. This creates an accretion disk, a swirling disk of superheated matter spiraling inward toward the black hole. The inner parts of this disk get extraordinarily hot, millions of degrees, hot enough to emit X-rays and even gamma rays. This radiation is what we actually detect when we observe black holes. The disk can shine brighter than entire galaxies, powered entirely by matter falling into the black hole. Some black holes also produce jets, narrow beams of particles and radiation shooting out perpendicular to the accretion disk. These jets can extend for thousands of light years, carrying enormous amounts of energy. They form when magnetic fields in the accretion disk channel some of the infalling material away from the black hole at nearly the speed of light. These are some of the most energetic phenomena in the universe. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. Actually, not the black hole itself, because you can't photograph something that emits no light, but the shadow of a black hole against the glowing accretion disk around it. The black hole at the center of galaxy Messier 87, about 53 million light-years away. The image shows a bright ring of emission with a dark center. That dark center is the black hole's shadow, and it's larger than our entire solar system. The black hole itself has a mass of about 6.5 billion times the mass of our Sun. 6,500 million solar masses compressed into a region smaller than the orbit of Neptune. The ring around it is the accretion disk, material spiraling inward at a significant fraction of light speed, heated to billions of degrees, glowing brightly in radio wavelengths. In 2022, they released a second image showing Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This one is much smaller, only about 4 million solar masses, but it's much closer, only about 26,000 light-years away, compared to 53 million for M87. Both images show the same basic structure, a bright ring with a dark shadow in the middle. The shadow is about 2.6 times larger than the actual boundary of the black hole, the event horizon, because light from behind the black hole gets bent around it by the intense gravity, creating a larger dark region than the event horizon itself. These images are remarkable achievements. requiring a network of radio telescopes spread across the entire Earth, working together to create a telescope effectively the size of the planet. But they only show us the outside. They show us the shadow, the accretion disk, the region around the black hole. They don't show us what's inside. And they can't, because information from inside a black hole can never reach us. That's what defines a black hole, the existence of a boundary called the event horizon from which nothing, not even light, not even information itself, can escape. So, what is this boundary? What is the event horizon? The simplest way to think about it is as the point of no return. Outside the event horizon, you can still escape if you have enough speed. A rocket with a powerful enough engine could blast away from the black hole and avoid falling in. But once you cross the event horizon, escape becomes impossible. Not just difficult, not just requiring more fuel, but actually, fundamentally, physically impossible. No amount of thrust, no amount of energy, nothing you could possibly do would allow you to escape. Why? Because inside the event horizon, all paths through space-time lead inward. There are no paths that lead outward. Not because something is pulling you in, though gravity is involved, but because the geometry of space-time itself has become so warped that outward simply doesn't exist as a direction anymore. This is where we need to talk about what Einstein's general relativity actually says about gravity. In Newton's theory, gravity is a force. Massive objects pull on each other across empty space. The sun pulls on Earth, Earth pulls on the moon, and so on. But Einstein showed that this isn't quite right. Gravity isn't a force in the traditional sense. It's a consequence of space-time curvature. Massive objects warp the fabric of space-time around them, and other objects move along curved paths through this warped space-time. Think of space-time as a flexible sheet. Place a heavy ball on the sheet, and it creates a depression. Roll a smaller ball near the depression, and it will curve toward the heavy ball, not because the heavy ball is pulling on it, but because the sheet itself is curved, and the small ball is just following the straightest possible path through the curved geometry. This is a common analogy, and like all analogies, it's imperfect. The rubber sheet model suggests gravity pulls things downward, which isn't quite right because there's no absolute down in space. But it captures the essential idea that massive objects curve space-time and objects move along paths determined by that curvature. A black hole takes this to the extreme. It curves space-time so severely that at the event horizon, the curvature becomes infinite in a certain mathematical sense. The paths through space-time, what physicists call world lines, all point inward inside the event horizon. There are no world lines that point outward. If you wanted to escape, you'd need to move faster than light along one of those inward-pointing world lines, and that's impossible. The speed of light is the universal speed limit. Nothing can exceed it. So once you're inside, you're trapped. The location of the event horizon depends on the black hole's mass. For a non-rotating black hole, which we call a Schwarzschild black hole after the physicist who first calculated its properties, the event horizon radius is given by a surprisingly simple formula. It's twice the gravitational constant times the mass divided by the speed of light squared. This radius is called the Schwarzschild radius. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. That means if you could somehow compress the entire Sun down to a sphere 3 kilometers in radius, about 1.8 miles across, it would become a black hole. The entire mass of the Sun, 330,000 times the mass of Earth, compressed into a ball smaller than a city. For a black hole with 10 solar masses, the Schwarzschild radius is about 30 kilometers. For Sagittarius A star at the center of our galaxy, with 4 million solar masses, the Schwarzschild radius is about 12 million kilometers, roughly the diameter of the Sun. For the monster black hole in M87, with 6.5 billion solar masses, the Schwarzschild radius is about 19 billion kilometers, larger than the orbit of Neptune. The larger the mass, the larger the event horizon. This might seem counterintuitive. You might think a more massive black hole would have stronger gravity and therefore a smaller event horizon. But the event horizon marks the point where escape velocity equals the speed of light, and that point moves outward as mass increases. Here's another surprising fact about black holes. The average density inside the event horizon actually decreases as the black hole gets larger. For a stellar mass black hole with 10 solar masses, the average density inside the event horizon is about 1.8 trillion kilograms per cubic meter. That's incredibly dense, far denser than any normal matter. For comparison, water has a density of 1,000 kilograms per cubic meter, and atomic nuclei have densities around 200 trillion kilograms per cubic meter. But for a supermassive black hole like M87, the average density inside the event horizon is only about 0.000001 kilograms per cubic meter. That's less dense than air, which is about 1.2 kilograms per cubic meter, much less dense than water. This doesn't mean the black hole is empty inside. All the mass is still there, but because the event horizon grows faster than the volume grows, the average density drops. For a black hole 1 billion times the mass of the Sun, the average density inside the event horizon would be similar to water. For a black hole 1 trillion solar masses, if such a thing existed, the average density would be less than the density of the air you're breathing right now. This seems strange until you remember that the event horizon isn't a physical surface. It's just a boundary in space-time beyond which escape is impossible. The actual matter of the black hole, whatever form it takes, is presumably all at the center in the singularity. The rest of the volume inside the event horizon is just severely warped space-time. Now let's talk about what happens when you actually fall into a black hole. Let's say you're approaching a stellar mass black hole, something with about 10 times the mass of the Sun. You're in a spacecraft, falling feet first toward the event horizon. What do you experience? First, the good news. As you approach the event horizon, from your perspective, nothing dramatic happens right away. You don't feel a sudden jolt or impact. The event horizon isn't a physical barrier like a wall. It's just a mathematical surface in space-time. You pass through it smoothly. In fact, at the exact moment you cross the event horizon, you might not even realize it's happened. There's no sign, no marker telling you that you've crossed the point of no return. But here's the bad news. Even before you reach the event horizon, you start to experience something called spaghettification. This is a real term, sometimes called the tidal effect, and it's one of the most violent aspects of falling into a black hole. Here's what happens. Gravity gets stronger as you get closer to the black hole. Your feet, which are closer to the black hole than your head, experience stronger gravitational pull than your head does. This difference in gravitational force between your feet and head is called a tidal force. The same principle causes ocean tides on Earth, where the moon pulls more strongly on the side of Earth facing it than on the far side. But near a black hole, these tidal forces become extreme. For a stellar mass black hole with 10 solar masses, by the time you're about 1,000 kilometers from the event horizon, the tidal forces are already uncomfortable. Your feet are being pulled noticeably harder than your head. By the time you're 100 kilometers away, the force difference is painful, like being stretched on a rack. By the time you're 10 kilometers away, the tidal forces are strong enough to tear your body apart. Your feet are being pulled so much harder than your head that the force overcomes the molecular bonds holding your body together. You get stretched lengthwise and compressed sideways, like being squeezed through a tube that's getting narrower and narrower. Eventually, you're not a human body anymore. You're a stream of atoms stretched out in a long, thin line, falling toward the singularity. This process happens faster and faster as you get closer. For a stellar mass black hole, you'd be torn apart well before reaching the event horizon. But here's something interesting. For a supermassive black hole, the situation is different. Because the event horizon is so much larger, the tidal forces at the event horizon are much weaker. Remember, tidal forces depend on how quickly gravity changes over distance. For a massive black hole, gravity changes more gradually because the event horizon is farther from the center. For a black hole with 1 billion solar masses, the tidal forces at the event horizon are comparable to the tidal forces you experience on Earth from the Moon. Negligible. You could cross the event horizon intact, still alive, still conscious, completely unaware that you've passed the point of no return. The spaghettification would come later, as you fall deeper inside and get closer to the singularity. But for a while, you'd be alive inside a black hole, able to observe your surroundings. What would you see? This is where things get really strange. As you approach the event horizon, you'd notice the light from the outside universe becoming distorted. The intense gravity bends light rays, so stars would appear in different positions than their true locations. Stars behind the black hole would appear above and around it, their light bent around the black hole by gravitational lensing. The black hole would appear as a dark sphere against the background of space, but surrounded by a bright ring of distorted starlight. As you get closer, this ring gets larger and brighter. More and more of the sky gets compressed into this ring as light from wider and wider angles gets bent around to reach your eyes. By the time you reach the event horizon, almost all the light from the outside universe is coming from this bright ring directly ahead of you. The rest of the sky is dark. If you looked back the way you came, you'd see all the stars and galaxies of the universe compressed into a smaller and smaller circle, getting brighter and brighter, blue shifted toward higher energies. Looking forward, toward the center of the black hole, you'd see darkness, pure, absolute darkness. No light from the outside universe can have fallen in ahead of you, because any light that crossed the event horizon before you did is already deeper inside, closer to the singularity, and it can't come back out to reach your eyes. Once you cross the event horizon, something profound changes. From the outside universe's perspective, time dilation effects near a black hole mean that you appear to slow down as you approach the event horizon. You get closer and closer, but never quite seem to cross. Your image gets redder and dimmer as the light leaving you gets stretched to longer wavelengths and takes longer and longer to escape the intense gravity. Eventually, you fade from view, your last photons stretched out over an infinite time. From the outside, you never quite cross the event horizon. You just fade away asymptotically. But from your perspective, time continues normally. You cross the event horizon in finite time, maybe a few seconds for a stellar mass black hole, maybe a few hours for a supermassive black hole, depending on how fast you're falling. And once you're inside, the rules change completely. Outside the event horizon, space and time behave normally. You can move through space in any direction, forward, backward, left, right, up, down. Time flows forward, from past to future. Inside the event horizon, space and time swap roles in a sense. The direction toward the singularity becomes time-like. Moving toward the singularity isn't a choice about where to go. It's as inevitable as moving forward in time. You can't stop moving toward the singularity any more than you can stop time from passing. Every moment that ticks by brings you closer to the center, regardless of what you do. You could fire your rockets at full power, pointing away from the singularity. It wouldn't matter. You'd still fall inward. Not because your rockets aren't powerful enough, but because inside the event horizon, all paths forward in time lead deeper inside. There are no paths that lead outward. Outward isn't a direction in space anymore, it's backward in time, and you can't travel backward in time any more than you could outside the black hole. This is what makes a black hole's interior so strange and terrifying. It's not that the gravity is pulling you inward, though that's part of it. It's that the structure of space-time itself has changed, so that inward is the only direction time allows. How long do you have after crossing the event horizon? For a non-rotating black hole with 10 solar masses, the time from crossing the event horizon to reaching the singularity at the center is about 0.0001 seconds, 1/10,000th of a second. You barely have time to register that you've crossed before. You're torn apart by tidal forces and smashed into the singularity. For a supermassive black hole with 1 billion solar masses, you'd have about 17 hours from crossing the event horizon to reaching the singularity. 17 hours to contemplate your fate, to experience being inside a region of space-time cut off from the rest of the universe, to watch the outside universe's history flash by in the bright circle of light behind you. Because from inside the event horizon, looking back, you'd see something remarkable. Time dilation works both ways. Just as observers outside see you slow down and never quite cross, you see the outside universe speed up. Events that take years or centuries outside happen in seconds from your perspective. You'd watch the universe age. Stars would be born and die. Galaxies would collide, all compressed into the hours or minutes or seconds you have left before reaching the singularity. It would be the ultimate time-lapse view of the cosmos, the entire future history of the universe playing out before your eyes in fast forward. Though by the time you're close enough to the singularity for the tidal forces to become severe, you'd probably be too distracted by being torn apart to appreciate the view. Now, let's talk about what's at the center of a black hole, the singularity. This is where things get truly weird and where our physics breaks down completely. According to general relativity, all the matter that fell into the black hole gets compressed into a single point of infinite density at the very center. Not a small point, not a tiny sphere, but an actual mathematical point with zero size. All the mass, all the matter, crushed into zero volume means infinite density. For a non-rotating black hole, the singularity is a point in space. For a rotating black hole, which is what most real black holes probably are, the singularity is a ring of zero thickness but finite radius where the density becomes infinite. This comes from the mathematics of general relativity. When you solve Einstein's equations for a rotating massive object collapsed beyond its event horizon. The rotation creates a centrifugal effect that prevents complete collapse to a point, instead forming a ring singularity. But whether it's a point or a ring, the singularity represents a place where general relativity predicts conditions that general relativity can't describe. Infinite density, infinite curvature of space-time, what physicists call a space-time singularity. At the singularity, the equations of general relativity break down. They give nonsensical answers, infinities that can't be physical. This tells us that general relativity is incomplete. It's an accurate description of gravity under most conditions, but at the extreme conditions inside a black hole, near the singularity, something else must be going on. We need a theory of quantum gravity, a theory that combines general relativity with quantum mechanics to understand what really happens. Several candidate theories exist: string theory, loop quantum gravity, others. But we don't have experimental evidence to distinguish between them. And we can't get such evidence because the singularity is hidden inside the event horizon where we can't see it. This is called cosmic censorship, the idea that singularities are always hidden inside event horizons, never naked and visible to the outside universe. If a naked singularity existed, it would be a place where physics breaks down that's visible and could affect the rest of the universe in unpredictable ways. So far, we've never observed one, and there are theoretical arguments suggesting they can't form under normal circumstances. But we don't have proof. It's an open question in theoretical physics. What we do know is that something strange happens at the singularity. Quantum effects that we usually ignore because they're so small compared to gravity must become important when densities and curvatures become extreme enough. One possibility is that quantum effects prevent the singularity from forming at all. Instead of infinite density, maybe there's a final state of matter at extreme but finite density. Another possibility is that the singularity represents a boundary where space-time itself ends. You fall in, you hit the singularity, and that's it. Time stops. Existence stops. You've reached the edge of space-time. We simply don't know. The singularity is hidden from view, and we can't build experiments to probe conditions of infinite density. We can only theorize and hope that someday we develop a consistent theory of quantum gravity that makes testable predictions about less extreme conditions. Let's talk about rotating black holes, because they're more interesting and probably more common than non-rotating ones. A rotating black hole, described by the Kerr metric, has some remarkable properties. It still has an event horizon, but the structure is more complex. There's an outer event horizon and an inner event horizon, with a region between them called the ergosphere. In the ergosphere, space-time is dragged around by the black hole's rotation. This is called frame dragging, and it happens around any rotating massive object, but it's extreme near a rotating black hole. Inside the ergosphere, you can't stay still relative to distant stars even if you wanted to. Space-time itself is rotating, and you're carried along with it. You have to orbit the black hole just to maintain your position. If you tried to remain stationary, you'd need to travel faster than light, which is impossible. But the ergosphere is still outside the event horizon. You can still escape from the ergosphere if you have enough thrust. The event horizon is deeper, closer to the center. Once you cross that, escape is impossible, just like with a non-rotating black hole. The interesting thing about the Kerr solution is the ring singularity. Unlike the point singularity of a non-rotating black hole, a ring singularity has a hole in the middle. This has led to speculation about what happens if you fall through the ring. Some solutions to Einstein's equations suggest you might emerge into a different region of space-time, possibly a different universe, or a different part of our own universe. This is pure speculation. The mathematics allows it, but the mathematics also allows many things that don't exist in reality. Most physicists think that quantum effects, which aren't included in these classical solutions, would prevent anything from actually passing through a ring singularity. The singularity would still be a place where space-time ends, where you're destroyed, just shaped differently than a point. But it's an interesting idea to think about. Rotating black holes can also extract energy in a remarkable way. There's a process called the Penrose process, where you can throw something into the ergosphere and extract rotational energy from the black hole. The object splits into two parts. One falls into the black hole, and the other escapes with more energy than the original object had. The energy comes from the black hole's rotation. The black hole spins down slightly, loses angular momentum, and the escaping object carries away energy. This is a real process, not speculation, and it might be happening around some black holes in nature. If a black hole is spinning rapidly and has material falling into it from an accretion disk, the interactions between the magnetic fields in the disk and the rotating space-time of the black hole can launch jets of particles at nearly the speed of light. These jets carry away enormous amounts of energy, much of it extracted from the black hole's rotation. Over time, this spins down the black hole. Eventually, if it continues long enough, without the black hole accreting more angular momentum, the black hole would stop rotating entirely and become a Schwarzschild black hole. But this takes an extraordinarily long time, far longer than the current age of the universe. Now let's talk about what black holes do to the universe around them and how they form in the first place. Black holes form when massive stars die. Not all stars, only the most massive ones. Stars like our Sun don't become black holes. When the Sun runs out of fuel in about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a dense ball of carbon and oxygen, about the size of Earth, but with the mass of the Sun. No black hole, but stars more massive than about 20 times the Sun's mass have a different fate. When they run out of fuel, their cores collapse catastrophically. The core is made of iron at this point, the end product of nuclear fusion. Iron can't be fused to release energy, so the core has no way to support itself against gravity. It collapses in a fraction of a second. Electrons are forced into protons, forming neutrons. The core becomes a ball of neutrons packed together as tightly as atomic nuclei. If the core's mass is less than about 2.5 to 3 solar masses, it stops collapsing at this point. You get a neutron star, an object about 10 miles across but with the mass of 1 to 2 suns. Unimaginably dense, with gravity so strong that escape velocity from the surface is about half the speed of light. But if the core is more massive than about 3 solar masses, even neutron degeneracy pressure can't hold it up. There's no known force that can stop the collapse. The core continues to shrink. It collapses through the neutron star density and keeps going. It forms an event horizon and becomes a black hole. The exact threshold for this is uncertain because the physics of matter at such extreme densities is not well understood. But somewhere between 2.5 and 3 solar masses, the transition happens. Below that, neutron star. Above that, black hole. The outer layers of the star, meanwhile, are falling inward. They hit the rebounding core or the newly formed black hole and bounce, creating a shockwave that blows the star apart. This is a supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. After the explosion, if the core was massive enough, a black hole remains at the center, typically with a mass of a few solar masses to a few dozen solar masses. This is a stellar mass black hole. We know of many such black holes in our galaxy. They're detected through their effects on nearby stars. If a star orbits an invisible companion and we can measure the star's motion, we can calculate the companion's mass. If the mass is more than 3 solar masses and we don't see any light from it, it's almost certainly a black hole. There are probably tens of millions of stellar mass black holes in our galaxy. Most are isolated, floating through space, essentially invisible. But some are in binary systems with normal stars, and those we can detect. Then there are supermassive black holes. These are millions to billions of times the mass of the Sun. They sit at the centers of galaxies. Nearly every large galaxy has one. Our Milky Way has Sagittarius A star, about 4 million solar masses. The Andromeda Galaxy has a black hole estimated at 100 to 200 million solar masses. Some galaxies have black holes exceeding 10 billion solar masses. How does supermassive black holes form? We don't fully understand this. They're too massive to form from a single star's collapse. The most massive stars that could exist are only a few hundred solar masses, and even those would lose much of their mass before collapsing. One possibility is that supermassive black holes form from the merger of many smaller black holes. A stellar mass black hole forms, accretes matter from its surroundings, grows larger, merges with other black holes, and over hundreds of millions or billions of years builds up to millions of solar masses. Another possibility is that they form from the direct collapse of massive gas clouds in the early universe. Instead of forming stars first and then black holes from those stars, maybe under certain conditions, a huge cloud of gas collapses directly into a black hole without ever forming a star. This could create black holes of thousands or tens of thousands of solar masses right from the start. Those seed black holes could then grow through accretion and mergers to become supermassive. We have evidence that supermassive black holes existed very early in the universe's history. We've detected quasars, extremely bright objects powered by matter falling into supermassive black holes, existing less than 1 billion years after the Big Bang. That's not much time for a black hole to grow from stellar mass to 1 billion solar masses. It suggests that the seeds were larger than stellar mass, or that they grew faster than we thought possible, or both. There's also a middle category called intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses. These are harder to detect than either stellar mass or supermassive black holes. We've found a few candidates, but the population and formation mechanisms are still uncertain. They might form from the merger of stellar mass black holes in dense star clusters, or they might be the seeds that grow into supermassive black holes. We're still figuring it out. Black holes don't just sit there, passive and unchanging. They interact with their surroundings in dramatic ways. Material falling into a black hole releases enormous amounts of energy. In fact, accretion onto a black hole is one of the most efficient energy conversion processes in the universe. Nuclear fusion, which powers stars, converts about 0.7% of mass into energy, 0.7%. Matter falling into a black hole can convert up to 40% of its mass into energy before crossing the event horizon. 40%. This happens because as matter spirals inward through the accretion disk, it loses gravitational potential energy. Some of that energy heats the disk, causing it to radiate. The closer to the black hole, the more energy can be extracted. For a rapidly rotating black hole, up to 42% of the infalling mass can be converted to radiation before the matter crosses the event horizon. This is why quasars and active galactic nuclei powered by supermassive black holes can shine so brightly. They're converting mass to energy with incredible efficiency, fed by steady streams of gas and dust falling into the black hole. A supermassive black hole accreting matter at a modest rate can outshine the entire galaxy of stars surrounding it. This accretion also affects the galaxy itself. The energy released heats gas in the galaxy, blowing it away from the central regions. This can shut down star formation by removing the raw material needed to make new stars. Many galaxies go through cycles where the central black hole is actively accreting and bright, heating the surrounding gas and suppressing star formation. Then the gas cools and falls back, feeding the black hole again. This feedback between the black hole and the galaxy is crucial to understanding how galaxies evolve. Without it, our models predict galaxies would form stars much more rapidly than we observe. The black hole at the center regulates the process, preventing runaway star formation. There's also a remarkable discovery from recent decades. The mass of a galaxy's central black hole correlates with properties of the galaxy itself, specifically with the mass of the galactic bulge and the velocity dispersion of stars in the bulge. This suggests that galaxies and their black holes grow together, co-evolving through mutual interactions. The black hole affects the galaxy through its energy output. The galaxy affects the black hole by feeding it gas and dust. They're not separate systems, they're linked. Understanding this connection is one of the major ongoing efforts in astrophysics. Let's talk about what happens when black holes merge. Since 2015, we've been able to detect gravitational waves, ripples in space-time itself, produced by accelerating masses. The first detection was from two black holes, each about 30 solar masses, spiraling into each other and merging. Since then, we've detected dozens of black hole mergers. Two black holes orbiting each other don't just continue orbiting forever. They gradually lose energy through gravitational wave emission. As they lose energy, their orbit shrinks. They spiral closer and closer together, orbiting faster and faster. This process takes a long time if they start far apart. Two black holes starting 1,000 miles apart might take billions of years to merge, but as they get closer, the process accelerates. In the final moments, they're orbiting each other many times per second, moving at a significant fraction of light speed. Then they merge. The event horizons touch and merge into a single, larger event horizon. The resulting black hole is slightly less massive than the sum of the two original black holes. Some of the mass has been converted to energy and radiated away as gravitational waves during the merger. This energy release is staggering. A typical black hole merger radiates more energy and gravitational waves in its final second than all the stars in the observable universe combined radiate in light. For that 1 second, the gravitational wave output of the merger exceeds the light output of the entire visible cosmos. The gravitational waves spread out from the merger site at the speed of light, stretching and compressing spacetime as they pass. When they reach Earth, they stretch and compress space by an incredibly tiny amount. The LIGO detectors that discovered gravitational waves measure changes in length about 1,000th the diameter of a proton across a 4-kilometer baseline. This is one of the most sensitive measurements ever made, detecting a signal that's been traveling for sometimes billions of years from events that happened across the universe. Supermassive black hole mergers are even more spectacular, though we haven't detected gravitational waves from those yet. When two galaxies merge, their central black holes eventually settle toward the center of the new combined galaxy. They form a binary system, two supermassive black holes orbiting each other. These systems are predicted to be loud sources of gravitational waves, but at much lower frequencies than stellar mass black hole mergers. Lower frequencies require much larger detectors. There are plans for space-based gravitational wave detectors that could detect supermassive black hole mergers, but they haven't been built yet. We have seen some candidate supermassive black hole binaries through indirect methods, observing peculiar behaviors in the centers of galaxies that suggest two black holes orbiting each other. When supermassive black holes finally merge, the resulting gravitational wave emission is so intense it can actually give the merged black hole a kick, sending it flying out of the galaxy center at speeds of hundreds or even thousands of kilometers per second. This happens because gravitational waves carry momentum. If they're emitted preferentially in one direction due to asymmetries in the merger, the recoil can be substantial. There's evidence for some of these recoiling black holes, supermassive black holes that have been kicked away from galaxy centers and are traveling through intergalactic space. Though they're hard to find because once they leave the gas-rich environment of the galaxy center, they stop accreting and become essentially invisible. Now let's address some common misconceptions about black holes, because they're some of the most misunderstood objects in the universe. First, black holes don't suck. They don't reach out and grab things. If you replace the Sun with a black hole of the same mass, Earth's orbit wouldn't change at all. We'd keep orbiting at the same distance, with the same period, completely unaffected except for the loss of sunlight. The gravitational pull from a black hole at any given distance is the same as the gravitational pull from any other object of the same mass at that distance. Black holes only become special when you get close enough to them that you'd be inside where the original object's surface was. At that point, you're closer to the center of mass, so gravity is stronger. If you could somehow get 10 kilometers from the center of the Sun, which you can't because the Sun's surface is much farther out than that, you'd experience much stronger gravity than Earth feels at 150 million kilometers distance. Same thing with a black hole. At a distance of 10 kilometers from a 10 solar mass black hole, Gravity is intense. But at Earth's distance, 150 million kilometers, it would be exactly the same as the Sun's gravity. Second misconception: black holes don't last forever. Stephen Hawking discovered in the 1970 seconds that black holes actually evaporate through a process called Hawking radiation. Quantum effects near the event horizon create particle-antiparticle pairs. Normally, these pairs annihilate immediately, but near a black hole's event horizon, sometimes one particle falls in while the other escapes. The escaping particle carries away energy. To conserve energy, the black hole must lose mass. Over time, the black hole evaporates. For stellar mass black holes, this process takes an unimaginably long time. A 10 solar mass black hole would take about 10 to the 67th years to evaporate. That's a 1 followed by 67 zeros. The universe is currently about 13.8 billion years old. That's roughly 10 to the 10th years. So it would take 10 to the 57 times the current age of the universe for a stellar mass black hole to evaporate. For supermassive black holes, it's even longer. A billion solar mass black hole would take 10 to the 92nd years to evaporate. These timescales are so long that they're essentially meaningless. The universe will be unrecognizably different long before then. All stars will have died. All normal matter will have decayed if protons are unstable, as some theories predict. The universe will be a cold, dark, empty place. But eventually, even black holes will evaporate through Hawking radiation. In the extreme far future, black holes might be the last structures remaining, slowly radiating away into nothing. Interestingly, as a black hole evaporates and loses mass, its temperature increases. Smaller black holes are hotter. A black hole with the mass of the Moon would have a temperature similar to the cosmic microwave background, about 3 Kelvin. A black hole with the mass of a large asteroid would be room temperature. A black hole with the mass of a mountain would be thousands of degrees. And a black hole with the mass of a few billion tons, about the mass of a large mountain, would be hot enough that its Hawking radiation includes visible light. It would glow white hot. As a black hole continues to shrink, it gets hotter and hotter, radiating energy faster and faster. The final moments of a black hole's evaporation would be explosive. A tiny black hole in its last second would release as much energy as millions of nuclear bombs. Then it would be gone, completely evaporated, leaving only the radiation it emitted. Of course, we've never observed this because stellar mass black holes are nowhere near the end of their evaporation process. They won't even start to noticeably shrink for tens of trillions of years. And smaller black holes, the ones that might evaporate sooner, probably don't exist. We don't know of any mechanism that would create black holes much smaller than stellar mass under normal circumstances. Third misconception: you can't see inside a black hole from the outside. This is true by definition. Information can't escape from inside the event horizon, so nothing inside can be observed from outside. But there's a related question that's more subtle. What happens to information that falls into a black hole? According to quantum mechanics, information can't be destroyed. It can be scrambled, mixed up, made practically impossible to recover, but fundamentally, it has to be preserved in some form. But according to general relativity, anything that falls into a black hole is gone forever, destroyed at the singularity. The information it carried is lost. This contradiction is called the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. Hawking initially argued that information is indeed destroyed in black holes, violating quantum mechanics. Later, he changed his position and argued that information must be preserved somehow, perhaps encoded in the Hawking radiation. But exactly how this works is still unknown. Some theories suggest that information is somehow stored on the event horizon itself in a holographic way. The event horizon is a two-dimensional surface, and maybe all the information about the three-dimensional interior is encoded on that surface. This is called the holographic principle, and it's a major area of research in theoretical physics. Other theories suggest that the paradox is resolved by quantum gravity effects that we don't yet understand. Maybe the singularity doesn't exist. Maybe black holes bounce and the information comes back out after an extremely long time. Maybe there are wormholes connecting the black hole to other regions of space-time. We don't know. Resolving the information paradox will probably require a complete theory of quantum gravity, which we don't have yet. Let's zoom out and think about what black holes mean for the universe as a whole. Black holes are endpoints of stellar evolution. They represent the final state of matter under conditions of extreme gravity. In a sense, they're inevitable. Gravity always pulls inward. For most objects, this is balanced by pressure. Planets are held up by the pressure of their rocks and metals. Stars are held up by the pressure from nuclear fusion. White dwarfs are held up by electron degeneracy pressure. Neutron stars are held up by neutron degeneracy pressure. But above a certain mass, no known pressure is enough. Gravity wins. The object collapses and forms a black hole. This makes black holes fundamental to understanding the long-term evolution of the universe. Given enough time, much of the matter in the universe will end up in black holes. Stars will form, live, die, and leave behind black holes. Those black holes will merge with other black holes, growing larger. Eventually, in the far future, the universe might consist mostly of black holes floating through empty space. And then, over truly astronomical timescales, those black holes will evaporate through Hawking radiation. The final state of the universe, in this scenario, is a thin soup of radiation with nothing substantial remaining. No stars, no planets, no black holes, just diffuse energy spreading out through infinite space, getting colder and more dilute forever. This is called the heat death of the universe, and it's one possible ending for the cosmos. Though we should note that our understanding of the universe's ultimate fate depends on things like dark energy that we don't fully understand. So, this is speculation based on current knowledge. Black holes also play a role in the largest structures in the universe. Galaxy clusters, the biggest gravitationally bound structures, often have giant elliptical galaxies at their centers. These galaxies have the most massive, supermassive black holes, sometimes exceeding 10 billion solar masses. These black holes affect the evolution of the entire cluster through their energy output. When they're actively accreting, they heat the gas filling the space between galaxies in the cluster, preventing it from cooling and falling into galaxies to form stars. This regulates star formation across millions of light years. We've also discovered that black holes might be responsible for some of the strange phenomena we observe in the universe. Fast radio bursts, brief flashes of radio waves from distant galaxies, might involve black holes, though other explanations are also possible. Gamma-ray bursts, the most energetic explosions in the universe besides the Big Bang itself, are thought to involve black holes forming from collapsing massive stars or from neutron star mergers. The jets produced by active galactic nuclei, powered by supermassive black holes, can extend for millions of light years and affect the evolution of entire galaxy clusters. Black holes are not just strange objects, they're active players in the cosmic drama, shaping the universe around them on every scale, from individual star systems to galaxy clusters. So what's inside a black hole? We've talked about the event horizon, the point of no return. We've talked about spaghettification, the tidal forces that tear matter apart. We've talked about the singularity, where general relativity breaks down and we don't know what happens. But is there anything else inside? Could there be structure, complexity, things happening between the event horizon and the singularity? For a non-rotating black hole, probably not much. The mathematics of the Schwarzschild solution is fairly simple. Once you're inside the event horizon, all paths lead to the singularity in a fraction of a second. There's no time for anything interesting to happen. But for a rotating black hole, things are more complex. The ring singularity creates a more complicated structure inside. There are multiple event horizons, inner and outer. The mathematics allows for some strange possibilities. Some solutions include closed time-like curves, paths through space-time that loop back on themselves, theoretically allowing time travel. Most physicists don't think these solutions represent reality. Quantum effects that aren't included in the classical mathematics probably prevent such exotic possibilities. But we can't be sure until we have a complete theory of quantum gravity. There's also speculation about what happens at the singularity. Does it represent an actual endpoint of space-time, or is it a place where our current theories break down but something else happens? Some theories suggest that the extreme conditions at the singularity might trigger the birth of a new universe, a new region of space-time that buds off from ours. Every black hole might be the seed of a new universe, expanding into its own space, with its own laws of physics potentially separate from and unobservable to our universe. This is highly speculative, not based on solid evidence, just on theoretical ideas about what quantum gravity might allow. But it's an intriguing possibility. Maybe the universe isn't just one space-time continuum. Maybe it's a branching structure with new universes forming inside black holes. Or maybe not. We simply don't know. The inside of a black hole remains one of the deepest mysteries in physics, a place where our best theories fail and we're forced to admit the limits of our knowledge. What we do know is that black holes are real. They exist. We've observed them, measured their masses, watched them merge, detected their gravitational waves. We've photographed their shadows. They're not speculation or mathematical curiosities. They're actual objects out there in space, governing the evolution of galaxies, marking the endpoints of stellar evolution, and challenging our understanding of the universe at the deepest level. Every black hole is a laboratory for extreme physics, a place where space-time itself is pushed to its limits. They test our theories in ways we can't replicate in any earthbound laboratory. No particle accelerator will ever reach the energy densities found near a black hole's singularity. No experiment will ever probe the curvature of space-time as severely as a black hole does naturally. So we study them from afar, using telescopes and gravitational wave detectors, building better theories, testing predictions, slowly piecing together an understanding of these most extreme objects. Let's come back to the practical question. What if you fell into a black hole? We've covered the physics, but what would the experience actually be like? Let's go through it step by step for a supermassive black hole where you'd survive crossing the event horizon. You're approaching in a spacecraft, falling freely toward the black hole. At first, from far away, the black hole is invisible. You might see stars, galaxies, the normal sky. But as you get closer, you start to notice distortions. Stars near the black hole appear in strange positions, their light bent by gravity. The black hole itself appears as a dark circle against the background stars. Around it, you see an Einstein ring, a bright circle of distorted starlight. As you get closer, this ring grows larger and brighter, encompassing more and more of your field of view. You look back toward wherever you came from, maybe Earth, and you see the universe there starting to compress into a smaller region of sky. Light from the universe outside is being bent around the black hole to reach you, so you can still see it, but it's increasingly distorted and blue-shifted. Blue-shifted means shifted toward higher frequencies, higher energies, because you're moving at high speed toward the black hole and away from the outside universe. Looking forward, toward the black hole, You see darkness, absolute blackness, because no light from the outside universe has fallen in ahead of you. You cross the event horizon. There's no physical sensation, no sudden change, but if you had a clock synchronized with one outside and could somehow compare them, you'd notice that time has changed. From the outside universe's perspective, you've frozen at the event horizon. But from your perspective, time continues normally. You've crossed the point of no return. Now you're inside. Looking back, you see the outside universe compressed into a bright, shrinking circle behind you. Because of time dilation effects, you're watching the outside universe age rapidly. Events that take years outside happen in seconds from your perspective. You see stars being born and dying, galaxies evolving, all compressed into a fast-forward view. Looking around, you see darkness in most directions. The only light comes from that circle behind you, showing the outside universe. And as you fall deeper, that circle gets smaller, brighter, more blue-shifted. Eventually, it's radiating at such high energies that it would kill you if you weren't shielded. But you're falling faster now. The tidal forces are starting to become noticeable, even in a supermassive black hole. Once you're far enough inside and close enough to the singularity, the tidal forces become severe. Your feet are being pulled harder than your head. The difference is subtle at first, just a slight stretching sensation, but it grows rapidly. Within hours or minutes, depending on the black hole's mass, the forces become painful, then unbearable, then fatal. Your body is stretched lengthwise and compressed sideways. Bones break, organs rupture, blood vessels tear. Eventually, you're no longer a coherent body, but a stream of atoms falling toward the center. And then you hit the singularity. What happens then? We don't know. Our equations give nonsense answers. Time ends, or becomes meaningless, or transforms into something we don't have words for. From the outside universe's perspective, you never reached the singularity because you never quite crossed the event horizon. You're frozen there, fading away, taking infinite time to complete the crossing. But from your perspective, it's over in finite time. You crossed, you fell, you reached the center, and then nothing, or something we can't describe with current physics. This is what's inside a black hole, a region of space-time where the normal rules break down, where gravity is so strong that it warps reality itself, where time and space exchange roles, and every path leads inevitably inward toward a singularity we can't understand. It's a place we can never visit and return from, never observe directly, never fully comprehend with our current theories. But we can study its effects, measure its properties from the outside, and continue building better theories to explain what happens in these most extreme environments. And that brings us to the end of this journey, into the heart of darkness. We've explored what black holes are, how they form, what happens at the event horizon, and the mysteries of the singularity. We've seen how black holes shape galaxies, how they merge and produce gravitational waves, and how they challenge our deepest understanding of space-time, information, and the nature of reality itself. Black holes are testaments to the extreme nature of the universe. They represent the limits of what gravity can do, pushing matter and space-time to their breaking points. They're laboratories for physics we can't replicate, experiments running naturally throughout the cosmos, and they remain, despite decades of study, among the most mysterious and fascinating objects in the universe. Every black hole is a trap with no escape, a one-way journey to the unknown, a place where physics as we know it ends and something else begins. They're frightening in their absolute finality, inspiring in their cosmic power, and humbling in how they expose the limits of human knowledge. We may never know what's truly at the center of a black hole. The singularity might remain forever beyond our understanding, hidden behind the event horizon, protected by the cosmic censorship that seems to prevent us from witnessing the breakdown of space-time. But we'll keep trying to understand. We'll build better detectors, observe more black holes, develop better theories of quantum gravity. We'll piece together clues from Hawking radiation, gravitational waves, and the behavior of matter falling into black holes. And maybe, someday, we'll finally understand what happens when gravity wins absolutely, when matter is compressed beyond all limits, when space-time itself curves back on itself and creates these singular points where our physics breaks down. Until then, black holes remain one of the universe's greatest mysteries, terrifying and beautiful, destructive and creative, representing both an end and perhaps, in ways we don't yet understand, a beginning. Thanks for journeying with me tonight into the depths of space-time, to the edge of the knowable universe, to the threshold of the singularity. Black holes may be traps with no escape, but understanding them, even from the outside, reveals truths about gravity, time, space, and the fundamental nature of reality that we couldn't learn any other way. And that's worth the journey, even if it's one we can only take in theory, with mathematics and observation, never with our own eyes. The universe is full of wonders, and black holes are among the most profound, places where the impossible becomes real and where our understanding must expand to match the cosmic scale of creation and destruction happening all around us. But there's so much more to explore about black holes. We've covered the basics, but let's dive deeper into some of the most fascinating aspects that make black holes truly unique in the cosmos. Let's talk about what time really means near a black hole, because the way time behaves in strong gravitational fields is one of the most counterintuitive aspects of relativity. We mentioned time dilation, but let's explore exactly what's happening and why. According to general relativity, time runs slower in stronger gravitational fields. This isn't just clocks running slow, it's time itself passing more slowly. Every physical process, every chemical reaction, every biological process, everything happens more slowly. Near a black hole's event horizon, this effect becomes extreme. If you're hovering just outside the event horizon, while your friend remains far away, your clock runs slower relative to your friend's clock. If you hover there for what feels like 1 hour to you, when you return to your friend, they might have aged years or decades or centuries depending on exactly how close to the event horizon you were. This is called gravitational time dilation, and it's been tested and confirmed with atomic clocks at different altitudes on Earth. Clocks at higher altitudes, where gravity is slightly weaker, run slightly faster than clocks at sea level. The difference is tiny, only about 10 nanoseconds per day for a clock at the altitude of GPS satellites, but it's measurable and real. GPS satellites have to account for this effect in their timing calculations, or they'd accumulate errors and navigation would fail. Near a black hole, the effect is vastly more extreme. Suppose you're in a spaceship hovering at a fixed distance from a black hole, using your rockets to maintain position and resist falling in. Your friend is far away in safe space, watching you through a telescope. You flash a light toward your friend once per second by your clock. But your friend doesn't see flashes arriving once per second. They see them arriving more slowly, maybe once every 2 seconds, or once every 10 seconds, or once every hour, depending on how close you are to the event horizon. This is because time in the strong gravitational field near the black hole is passing more slowly relative to time in your friend's weaker gravitational field. Your 1 second is longer than your friend's 1 second. When measured by the same standard, from your perspective, nothing seems wrong. Your clock ticks normally, your heartbeat is normal, you're breathing normally. But from your friend's perspective, watching from afar, you've slowed down. Your movements appear sluggish. Your clock appears to tick slowly. If you could somehow maintain this position indefinitely, and your friend watched you for what seems like a year to them, you might have only experienced a week, or a day, or an hour, depending on the strength of the gravitational field. Now suppose you get even closer to the event horizon. At a certain distance, called the photon sphere, light itself can orbit the black hole in circular paths. This is about 1.5 times the Schwarzschild radius for a non-rotating black hole. At this distance, time dilation is already severe. One of your seconds might correspond to several seconds or minutes for your distant friend. Get even closer, within a few percent of the event horizon radius, and time dilation becomes absurdly large. One of your seconds might correspond to days or years for your friend. At the event horizon itself, time dilation becomes infinite. An outside observer would see you frozen, never quite crossing, your last moments stretched out over infinite time. But you would cross in finite time by your own clock and experience the finite journey to the singularity. This creates a strange paradox. From the outside, nothing ever crosses the event horizon. The universe ends before anything finishes falling in. But from the infalling perspective, crossing happens in finite time. Both perspectives are valid. They're just describing different coordinate systems, different ways of slicing up space-time into space and time. This is one of the deep lessons of relativity, that space and time aren't absolute. They depend on your motion and the gravitational fields you're in. Let's explore the mathematics of black holes a bit more, because the equations that describe them are remarkably elegant despite describing such extreme physics. The Schwarzschild solution to Einstein's field equations describes a non-rotating, uncharged black hole. It's one of the simplest exact solutions to Einstein's equations, found by Carl Schwarzschild in 1916, just months after Einstein published General Relativity. Schwarzschild was a German physicist and astronomer serving in the German army during World War I. Despite being in the trenches, he worked on Einstein's equations and found this exact solution describing the spacetime geometry around a spherical mass. He sent his solution to Einstein, who was amazed that someone had found an exact solution so quickly. Schwarzschild died later that year from a disease he contracted during the war, but his solution became one of the foundational results in general relativity. The Schwarzschild metric describes how distances and times are measured near a spherical mass. It includes the Schwarzschild radius, which marks the event horizon for a black hole. Inside this radius, the roles of space and time swap in a certain mathematical sense. The radial direction toward the center becomes time-like, meaning you must move toward the center, just as you must move forward in time. You can't stay at a fixed radius inside the event horizon any more than you can stop time from passing. And the time direction becomes space-like, meaning you could in principle move forward or backward in time if the singularity weren't in the way. Though you can't, because all paths lead to the singularity first. This role reversal is part of what makes the black hole interior so strange. The rules that govern what's possible and what's not have changed. The Kerr solution, found by Roy Kerr in 1963, describes a rotating black hole. It's considerably more complex than the Schwarzschild solution, but it's more realistic because most black holes in nature probably rotate. When a massive star collapses, it almost certainly has some rotation, and that rotation is conserved, concentrating into a smaller and smaller radius as the core collapses. By conservation of angular momentum, a slowly rotating massive star becomes a rapidly rotating black hole. The Kerr solution includes features like the ergosphere and the ring singularity that we discussed earlier. It also describes how spacetime is dragged around by the black hole's rotation, an effect called frame dragging or the Lense-Thirring effect. This has been measured around Earth using satellites, confirming that rotating masses do indeed drag spacetime around with them. Near a rotating black hole, this effect is extreme. close to the event horizon, spacetime is being dragged around so fast that you'd have to travel faster than light to remain stationary relative to distant stars. You're forced to orbit the black hole just to stay in place. There's also a solution for a charged black hole called the Reissner-Nordstrom solution, but this is probably not very relevant to real black holes. Any significant electric charge on a black hole would quickly attract opposite charges from the surrounding environment and neutralize. In practice, black holes are probably neutral or very nearly neutral electrically. The most realistic solution for actual black holes is the Kerr-Newman solution, which describes a rotating, charged black hole. But as I mentioned, the charge is probably negligible, so Kerr is the most important for astrophysics. These solutions are exact mathematical solutions to Einstein's field equations, meaning they describe the space-time geometry perfectly under the assumptions of general relativity. They're not approximations or numerical simulations, they're exact answers. This is rare in physics. Most problems in general relativity don't have exact solutions. We have to use approximations or computers to solve them. But black holes are symmetric enough that exact solutions exist, and these solutions have been tested against observations and found to be accurate. Now, let's discuss black hole thermodynamics, because black holes have temperature, entropy, and other thermodynamic properties, which seems bizarre for objects that classically absorb everything and emit nothing. Jacob Bekenstein, in the early 1970s, proposed that black holes have entropy proportional to the area of their event horizons. This was controversial at the time because entropy is associated with disorder, with the number of possible internal states of a system. But black holes were thought to be completely featureless, described entirely by their mass, charge, and angular momentum, the so-called no-hair theorem. A black hole has no hair, meaning no additional features or structure beyond those three numbers. All information about what fell in is lost, or so it seemed. So how could a black hole have entropy if it has no internal states? Bekenstein argued that the entropy should be proportional to the surface area of the event horizon, because of arguments involving the generalized second law of thermodynamics. If you throw matter with entropy into a black hole, the total entropy in the universe must not decrease. The black hole must gain entropy to compensate for the entropy of the matter that fell in. The only reasonable quantity that always increases when you add mass to a black hole is the surface area of the event horizon. So Bekenstein proposed that black hole entropy is proportional to area. Then Stephen Hawking calculated Hawking radiation in 1974 and found that black holes emit thermal radiation with a temperature inversely proportional to their mass. This confirmed that black holes have temperature, and using the laws of thermodynamics, Hawking could calculate the entropy precisely. It turns out to be exactly what Bekenstein proposed, proportional to the area of the event horizon. Specifically, the entropy is the area of the event horizon in Planck units divided by 4. This is a huge number for any macroscopic black hole. A solar mass black hole has an entropy of about 10 to the 54th times Boltzmann's constant. For comparison, the Sun itself, a hot ball of plasma, has an entropy of about 10 to the 58th times Boltzmann's constant. So a black hole has less entropy than the star that formed it, which seems strange until you remember that as the black hole evaporates through Hawking radiation, it emits high entropy radiation. The total entropy of the black hole plus the radiation it emits over its entire lifetime is much larger than the entropy of the original star. The second law is preserved. This connection between black holes and thermodynamics is profound. It suggests that black holes are not featureless after all, that there are a vast number of quantum states corresponding to a black hole of a given mass, and that these states are somehow encoded in the structure of the event horizon. This led to the holographic principle, The idea that all the information about a three-dimensional volume of space can be encoded on the two-dimensional surface that bounds it. The black hole is the prime example. All the information about what fell into the three-dimensional volume inside the event horizon is encoded on the two-dimensional event horizon surface. This principle has been extended to suggest that the entire universe might be holographic, that everything we experience in three dimensions of space might be encoded on a distant two-dimensional surface. This is speculative but taken seriously by theoretical physicists working on quantum gravity. Let's talk about what we've actually observed when it comes to black holes, because until recently, black holes were largely theoretical objects. We had strong indirect evidence, but no direct observations. That changed in the last few decades. With advances in observational astronomy, we've detected black holes through several methods. First, X-ray binaries. These are systems where a black hole orbits a normal star. Matter from the star is pulled onto an accretion disk around the black hole. As it spirals inward, it heats up and emits X-rays. By measuring the X-rays and the motion of the visible star, we can determine the mass of the invisible companion. If it's more than about 3 solar masses and emits no light of its own, it's almost certainly a black hole. Cygnus X1 was one of the first confirmed black hole candidates, discovered in 1964 and confirmed as a black hole in the 1,970 seconds. It's about 15 solar masses orbiting a blue supergiant star about 6,000 light-years away. The star is being slowly consumed by the black hole, losing mass that spirals into the accretion disk. Since then, we've found dozens of X-ray binaries likely containing black holes in our galaxy. Second, we observe the centers of galaxies. By tracking the orbits of stars near the galactic center, we can infer the presence of a massive invisible object. In the case of our own Milky Way, stars near the center orbit an invisible object at the position of Sagittarius A star with orbital periods of years to decades. By measuring these orbits precisely, we can calculate the mass of the central object. It's about 4 million solar masses contained in a region smaller than the orbit of Mercury. The only plausible explanation is a supermassive black hole. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize in Physics for this work, tracking stars orbiting the Milky Way's central black hole over decades to prove its existence. There's one star called S2 that orbits the black hole every 16 years, reaching speeds of about 3% of light speed at its closest approach. Observing this star's orbit has allowed incredibly precise tests of general relativity in the strong gravitational field near the black hole. General relativity passes these tests with flying colors. Third, we detect gravitational waves from merging black holes. LIGO and Virgo, the gravitational wave observatories, have detected dozens of black hole mergers since their first detection in 2015. The signal is distinctive, a chirp that increases in frequency and amplitude as the black holes spiral together, then a sudden cutoff when they merge. By analyzing this signal, we can determine the masses of the black holes, their spins, the distance to the merger, and other properties. This has opened an entirely new way of observing the universe, not through light, but through ripples in space-time itself. And fourth, we've imaged the shadows of supermassive black holes using the Event Horizon Telescope. The images of M87 star and Sagittarius A star show the dark shadow surrounded by bright emission from the accretion disk. These images confirm that the objects at the centers of these galaxies have the properties expected of black holes, specifically an event horizon creating a shadow. No other known object would create this shadow. Each of these methods provides complementary information. X-ray binaries tell us about stellar mass black holes and how they interact with companion stars. Galactic center observations tell us about supermassive black holes and test general relativity. Gravitational waves tell us about black hole mergers and the properties of spacetime, and direct imaging confirms the existence of event horizons. Together, they build an overwhelming case that black holes are real, that they exist in nature, and that they behave as Einstein's equations predict. Let's explore some of the exotic possibilities that physics allows for black holes, even if we don't know whether these possibilities occur in nature. White holes are the time reverse of black holes. Instead of a region that nothing can escape from, a white hole would be a region that nothing can enter. Matter and energy would emerge from a white hole, but couldn't fall in. The mathematics of general relativity allows white holes as valid solutions to Einstein's equations. They're the past time reverse of black holes. But we've never observed one, and there are good reasons to think they don't exist in our universe. For one thing, they'd be incredibly unstable. Even a tiny amount of matter falling toward a white hole would disrupt it. And there's no known process that would create a white hole. Black holes form from gravitational collapse, but white holes would require a region of spacetime that spontaneously expels matter, which doesn't happen as far as we know. Some speculations connect white holes to the Big Bang, suggesting that the Big Bang might be viewed as a kind of white hole, a singularity from which all matter and energy emerged. But this is highly speculative. Wormholes are another exotic possibility allowed by the mathematics of general relativity. A wormhole would be a tunnel through spacetime connecting two different regions, possibly two different points in our universe, or possibly two entirely different universes. You could enter one mouth of the wormhole and emerge from the other mouth at a distant location or time. This sounds like science fiction, and indeed it appears in countless sci-fi stories, but the mathematics allows it under certain conditions. The problem is, those conditions, to keep a wormhole open, you need exotic matter with negative energy density. This is matter that has less than zero energy, which sounds impossible, but quantum field theory does allow states with negative energy density under certain conditions, like the Casimir effect between conducting plates. However, it's unclear whether you can accumulate enough negative energy to stabilize a wormhole large enough to travel through. Most physicists suspect that quantum effects would cause any wormhole to collapse before you could use it. There are also issues with causality if wormholes allow time travel, creating potential paradoxes. It's an active area of research, but don't expect wormhole travel anytime soon, if ever. Another exotic idea is the fuzzball proposal from string theory. Instead of a singularity at the center of a black hole, string theory suggests the entire interior might be filled with a dense tangle of strings and brains, a fuzzball with no actual singularity. The event horizon would still exist, but the interior structure would be different from what general relativity predicts. This might resolve the information paradox, because information falling into a black hole would be encoded in the structure of the fuzzball rather than lost at a Stark's singularity. But this is speculative, based on string theory, which itself isn't fully confirmed. We don't have observational evidence for or against fuzzballs. From the outside, a fuzzball black hole would look identical to a classical black hole, so we can't distinguish them observationally. There's also the idea of primordial black holes that formed in the early universe, not from stellar collapse, but from density fluctuations shortly after the Big Bang. These could have any mass, from tiny micro-black holes much smaller than an atom to massive black holes larger than stars. Some theories suggest primordial black holes might make up some or all of the dark matter in the universe. Dark matter is the mysterious, invisible matter that makes up about 85% of all matter in the universe, known to exist from its gravitational effects, but never directly detected. If dark matter is made of primordial black holes, that would solve the dark matter mystery and explain why we haven't detected dark matter particles in laboratory experiments. However, observations have constrained this possibility significantly. We've looked for signatures that primordial black holes would leave, and we haven't found them in most mass ranges. There are still some allowed windows where primordial black holes could exist, but they probably don't make up all the dark matter. Maybe a small fraction, but probably not the majority. Let's discuss what happens near a black hole from the perspective of quantum mechanics, because there are fascinating effects that occur when you combine quantum physics with the extreme gravity near a black hole. The Unruh effect, discovered by William Unruh in 1976, predicts that an accelerating observer sees a thermal bath of particles even in a vacuum. This is related to Hawking radiation. If you're accelerating in a spaceship in empty space, you'd detect a faint background of thermal radiation with a temperature proportional to your acceleration. The vacuum of space isn't the same for accelerating observers as for inertial observers. Near a black hole's event horizon, the acceleration needed to hover at a fixed position is enormous, approaching infinity as you get closer to the horizon. This means a hovering observer near the horizon would experience intense Unruh radiation. They'd be bathed in high-energy particles created by their own acceleration. This is different from Hawking radiation, which is emitted by the black hole itself, but it's related through the equivalence principle that links acceleration and gravity. Quantum mechanics also predicts that particle-antiparticle pairs are constantly being created and annihilated in empty space. These are called virtual particles, and they exist for such short times that they don't violate conservation of energy. Near a black hole's event horizon, these virtual pairs can be separated. One particle falls into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. This is the mechanism behind Hawking radiation. From the black hole's perspective, it's emitting thermal radiation and slowly losing mass. From the perspective of quantum field theory, it's virtual particles at the horizon becoming real through the interaction with the event horizon. Another quantum effect near black holes is the firewall paradox. This is a recent puzzle in black hole physics, proposed in 2012 by Almheri, Maroff, Polchinski, and Sully. The paradox arises from trying to reconcile quantum mechanics, general relativity, and the requirement that information not be destroyed. If information falling into a black hole must be preserved and must eventually come out in Hawking radiation, and if Hawking radiation is thermal, which means it carries no information about what fell in, then there's a contradiction. One proposed resolution is that the event horizon is actually a firewall, a region of extremely high energy that destroys anything crossing it. This would violate the equivalence principle, which says that free fall should be indistinguishable from floating in empty space. Near a black hole, this means crossing the event horizon should be smooth, not violent. But the firewall idea suggests it's not smooth, that there's actually a violent event at the horizon that destroys information physically. This has sparked intense debate among physicists. Some argue that firewalls can't exist because they violate basic principles of relativity. Others argue that the information paradox forces us to accept that something dramatic happens at the horizon. Still others propose different resolutions, like the idea that quantum entanglement between the interior and exterior of the black hole might allow information to escape without violating the no communication theorem from quantum mechanics. This is an active area of research, and we don't have a consensus resolution yet. It's possible that solving the firewall paradox will require new insights into quantum gravity that we don't currently have. Let's talk about the different types of black holes in more detail, because there's actually a surprising variety depending on how they form and where they are. Stellar mass black holes, as we've discussed, form from collapsing massive stars. They typically range from about 3 solar masses, the minimum mass to form a black hole, up to perhaps 100 solar masses. Stars more massive than about 100 solar masses are unstable and lose mass through powerful stellar winds before they can collapse. So there's probably an upper limit to stellar mass black holes, around 50 to 100 solar masses, though the exact limit is uncertain. Within the Milky Way, we estimate there are about 100 million to a billion stellar mass black holes, most of them isolated and invisible, drifting through the galaxy as remnants of ancient massive stars. Only a tiny fraction are in binary systems, where we can detect them through X-rays or gravitational waves. Intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses, are more mysterious. We're not entirely sure how they form. One possibility is runaway collisions in dense star clusters. In the center of a globular cluster, a dense ball of hundreds of thousands of stars. Collisions between stars might be common enough to build up a massive star that then collapses into a black hole. This black hole could then grow by accreting more stars, eventually reaching thousands of solar masses. Another possibility is that intermediate mass black holes are the seeds that grow into supermassive black holes. Maybe they form in the early universe through direct collapse of gas clouds, then grow through accretion and mergers over billions of years. We've found some candidate intermediate mass black holes, but confirming their existence and properties is difficult because they're less common and harder to detect than either stellar mass or supermassive black holes. Supermassive black holes, millions to billions of solar masses, sit at the centers of most large galaxies. They're too massive to form from stellar collapse, and they formed too early in the universe's history to grow from stellar mass seeds purely through accretion. The leading theories involve either rapid growth from intermediate mass seeds through super-Eddington accretion, where matter falls in faster than standard models predict, or direct collapse of massive gas clouds in the early universe, creating large seed black holes that then grow more conventionally. We know that supermassive black holes existed less than 1 billion years after the Big Bang because we've detected quasars, extremely bright objects powered by black holes at those early times. This is a puzzle because there wasn't much time for a stellar mass black hole to grow to billions of solar masses through normal processes. Either the seeds were larger than stellar mass, or they grew faster than we think should be possible, or both. This is an active area of research. New telescopes like the James Webb Space Telescope are observing the very early universe to find these early black holes and understand how they formed and grew so quickly. Then there are micro black holes, hypothetical black holes, much smaller than stellar mass. These couldn't form from stellar collapse because there's no way to compress matter to the required density during star formation. But they might have formed in the early universe if there were large density fluctuations shortly after the Big Bang, and they might be produced in high-energy particle collisions, though this is extremely speculative and there's no evidence for it. Some theories involving extra dimensions predict that micro black holes could be produced at CERN's Large Hadron Collider. These black holes would evaporate essentially instantly through Hawking radiation, producing a distinctive signature of particles. No such signature has been seen, which constrains theories about extra dimensions. If micro black holes exist, the tiny ones would have evaporated by now through Hawking radiation. Only micro black holes, larger than about 10 to the 15th grams, about the mass of a small mountain, would still exist today. Smaller ones would have evaporated over the 13.8 billion years since the Big Bang. Let's explore the connection between black holes and the large-scale structure of the universe. Because black holes don't exist in isolation, they're intimately connected to the evolution of galaxies and the cosmos. Every large galaxy has a supermassive black hole at its center, and the mass of this black hole correlates with properties of the galaxy. This is surprising because the black hole makes up only a tiny fraction of the galaxy's mass. Sagittarius A star is 4 million solar masses, but the Milky Way contains about 200 billion solar masses of stars. The black hole is only about 0.002% of the galaxy's mass. Yet there's a tight correlation between the black hole's mass and the mass of the galactic bulge, the dense central region of old stars. There's also a correlation with the velocity dispersion of stars in the bulge, a measure of how fast stars are moving randomly. These correlations are known as the M-sigma relation, and they're remarkably tight. If you measure the velocity dispersion of a galaxy's bulge, you can predict the mass of the central black hole to within a factor of 2 or 3. This suggests that the black hole and the galaxy grow together, co-evolving through some process that links their growth. One mechanism is feedback from active galactic nuclei. When a black hole is accreting matter rapidly, it releases enormous amounts of energy. This energy heats gas in the galaxy, blowing it away from the central regions. This limits star formation because the gas needed to make stars has been heated and expelled. Without this feedback, galaxies would form stars much more rapidly than observed, exhausting their gas supply quickly. The black hole regulates the process, keeping the galaxy from forming stars too fast. This feedback also limits the black hole's own growth, because blowing away the gas removes the material the black hole would otherwise accrete. So there's a self-regulating cycle where the black hole and galaxy reach an equilibrium. On even larger scales, black holes affect the structure of galaxy clusters. The most massive galaxies in clusters often have the most massive black holes, exceeding 10 billion solar masses. These black holes produce jets and outflows that heat the gas filling the space between galaxies in the cluster. This gas, called the intracluster medium, is extremely hot, millions of degrees, and it emits X-rays that we can detect. The energy from the central black hole prevents this gas from cooling and falling into galaxies to form stars. Without this heating, the gas would cool, fall inward, and form trillions of new stars over time. But we observe that star formation in cluster galaxies is actually suppressed compared to galaxies outside clusters. The black hole feedback is a major reason why. This means black holes have shaped the evolution of the universe on the largest scales. They've regulated star formation, influenced the structure of galaxies and clusters, and determined the distribution of matter throughout the cosmos. The universe would look very different without black holes. Galaxies would be smaller, denser, with more stars and less gas. Clusters would be brighter in X-rays, with cooler, denser centers. The overall structure of the cosmic web, the large-scale distribution of galaxies and dark matter, might be different as well. Now let's address one of the most profound questions about black holes. Do they destroy information? This is the black hole information paradox, one of the deepest problems in theoretical physics, at the intersection of quantum mechanics, general relativity, and thermodynamics. Here's the problem. Quantum mechanics is fundamentally reversible. If you know the quantum state of a system at one time, you can calculate its state at any other time, forward or backward. Information is conserved. No physical process can destroy information in quantum mechanics. It can only be scrambled or transformed. But according to general relativity, anything that falls into a black hole is gone forever, compressed into the singularity where our physics breaks down. The information about what fell in seems to be lost, destroyed. This creates a contradiction. Quantum mechanics says information must be conserved. General relativity says information falling into a black hole is lost. Both theories can't be completely correct, as stated. Hawking radiation makes the problem even more acute. Black holes evaporate over extremely long times, slowly radiating away their mass. If the Hawking radiation is purely thermal, it carries no information about what fell into the black hole. When the black hole finally evaporates completely, the information about everything that fell in over the black hole's lifetime has disappeared. This would violate quantum mechanics. So where does the information go? Several possibilities have been proposed. One is that Hawking radiation isn't purely thermal after all. Maybe it contains subtle correlations that encode the information about what fell in. The information comes out in the radiation, but in such a scrambled form that it's essentially impossible to recover. This is called the information being hidden in correlations. Another possibility is that information doesn't escape until the very end of the black hole's evaporation. It's stored somehow in the black hole's structure, perhaps in the event horizon, and then released in a final burst when the black hole evaporates completely. This is called the remnant scenario, where a tiny stable remnant is left over after evaporation containing all the information. A third possibility is that information is transferred to another region of spacetime through quantum entanglement or through a wormhole. Maybe the interior of the black hole is connected to the exterior or to another universe in ways we don't understand. String theory offers some insights through the AD-SCFT correspondence, a mathematical relationship between quantum gravity in certain spacetimes and quantum field theory on the boundary of those spacetimes. In this framework, information is preserved because the system has a dual description where information conservation is manifest. But applying this to realistic black holes in our universe is still an open problem. Recent work on the Page curve has shed some light on the problem. The Page curve describes how the entropy of Hawking radiation changes as a black hole evaporates. Initially, the entropy of the radiation increases as more radiation is emitted, but at a certain point, the entropy must start decreasing to ensure that total entropy is conserved. This is called the Page time, roughly halfway through the black hole's evaporation. Calculating this curve correctly requires accounting for quantum entanglement between the black hole and the radiation in subtle ways. Recent work, using ideas from quantum information theory and holography, has successfully reproduced the expected Page curve, suggesting that information is indeed preserved, though the mechanism isn't fully understood. This is an active research area, and a complete resolution of the information paradox will likely require a full theory of quantum gravity. Understanding how information is preserved in black hole evaporation would be a major breakthrough, potentially revealing deep truths about the nature of spacetime and quantum mechanics. Let's talk about what black holes tell us about the fundamental nature of reality, because they're more than just exotic astronomical objects. They're laboratories for testing our deepest theories about the universe. Black holes are places where quantum mechanics and general relativity clash. General relativity describes gravity as the curvature of spacetime, and it works beautifully on cosmic scales. Quantum mechanics describes the behavior of matter and energy on the smallest scales, and it works beautifully for atoms and particles. But these two theories are incompatible at a fundamental level. General relativity is a classical theory, meaning it doesn't include quantum effects. Quantum mechanics is a quantum theory, obviously, but it treats spacetime as a fixed background, not something that can curve and flex. At the singularity of a black hole, both quantum effects and gravitational effects are strong. You can't ignore either one. But we don't have a consistent theory that combines them. General relativity predicts a singularity with infinite curvature. Quantum mechanics suggests that something else should happen at such extreme densities, preventing the infinity. This is why black holes are so important for fundamental physics. They force us to confront the limitations of our current theories. They tell us that something is missing, that we need a theory of quantum gravity to fully understand them. Several candidate theories exist, as I mentioned earlier. String theory replaces point particles with tiny vibrating strings, and it naturally includes gravity, along with the other forces. It requires extra dimensions of space beyond the three we experience, and it makes predictions about black holes, including the fuzzball structure I mentioned. Loop quantum gravity takes a different approach, quantizing space-time itself, treating space as a network of discrete quantum loops. In this theory, the singularity might be replaced by a quantum bounce, where the collapsing matter reaches a minimum size, then expands again, possibly creating a new universe. Other approaches include causal set theory, asymptotic safety, and emergent gravity scenarios. Each has its strengths and challenges, and we don't yet know which, if any, is correct. What we do know is that black holes provide crucial clues: their thermodynamic properties, the behavior of Hawking radiation, the information paradox. These are all constraints that any successful theory of quantum gravity must satisfy. When we eventually develop a complete theory, it will have to reproduce everything we know about black holes from observation and from the partial theories we have now. Black holes also tell us something profound about the nature of space-time. The fact that the event horizon is a real boundary beyond which no information can pass suggests that space-time has a structure, that it's not just a smooth continuum, but has physical properties that can be probed. The holographic principle, which emerged from black hole thermodynamics, suggests that space-time might be emergent, not fundamental. Maybe the three dimensions of space we experience arise from a more fundamental two-dimensional description on a distant surface. This is a radical idea, that space itself might not be fundamental but might emerge from deeper quantum information theoretic principles. And it comes directly from thinking about black holes. Black holes also raise questions about the nature of time. At the singularity, our understanding of time breaks down. It's not just that clocks stop working, it's that the concept of time itself becomes meaningless. Inside the event horizon, time and space swap roles in a sense, and at the singularity, both might cease to exist in any recognizable form. This suggests that time, like space, might not be fundamental. Maybe time emerges from something more basic, something that doesn't look like time at all. These are deep philosophical questions as much as scientific ones. What is space? What is time? What is the ultimate nature of reality? Black holes force us to confront these questions because they're places where space and time behave in ways that challenge our intuitions and our theories. Let's talk about the future of black hole research, because we're in a golden age of black hole astronomy, with new discoveries happening regularly. The detection of gravitational waves has revolutionized the field. Before 2015, black hole mergers were theoretical predictions. Now they're observed regularly. We've detected dozens of stellar mass black hole mergers, measuring their properties and testing general relativity in the strong field regime. Future gravitational wave detectors will be even more sensitive. The space-based LISA mission, planned for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. These mergers produce lower-frequency gravitational waves that can't be detected by ground-based detectors like LIGO because seismic noise on Earth drowns them out. But in space, without seismic noise, LISA will be able to detect these signals from across the universe. This will give us a census of supermassive black hole mergers, telling us how common they are, how black holes grow, and how galaxies evolve. The Event Horizon Telescope is also improving. Future observations will image more black holes with higher resolution. We might see movies of the gas swirling around black holes in real time, observe the launching of jets, and test general relativity's predictions about the shape and size of event horizons. There are also plans for next-generation EHT arrays that would include radio telescopes in space, increasing the baseline even further and allowing even sharper images. We might eventually be able to image stellar mass black holes, not just supermassive ones. New telescopes across the electromagnetic spectrum will reveal more about black holes' environments. The James Webb Space Telescope is finding black holes in the early universe, telling us how they formed and grew. X-ray telescopes are mapping the hot gas around black holes, revealing how they affect their surroundings. Radio telescopes are detecting jets and outflows, showing how energy is transported away from black holes across vast distances. On the theoretical side, progress in quantum gravity might finally resolve the information paradox and tell us what's really at the center of a black hole. Advances in computational power allow more detailed simulations of black hole mergers, accretion disks, and jet formation. These simulations help us interpret observations and make predictions for future detections. There's also interest in searching for primordial black holes as dark matter candidates. New surveys might detect them through gravitational microlensing, where a black hole passing between us and a distant star briefly brightens the star's light. If dark matter consists partly of primordial black holes, we should be able to detect this. And there's always the possibility of unexpected discoveries. Black holes have surprised us before, and they'll likely surprise us again. Maybe we'll find intermediate mass black holes and understand how they form. Maybe we'll detect black holes in binary systems with other exotic objects like neutron stars or white dwarfs. Maybe we'll find evidence for alternatives to black holes, exotic compact objects that behave similarly but have different properties. Every new observation has the potential to reveal something unexpected about these most extreme objects in the universe. So where does this leave us? Black holes are real, they're common, and they're crucial to understanding the universe. They form from collapsing stars, sit at the centers of galaxies, merge to produce gravitational waves, and challenge our understanding of physics at the most fundamental level. Inside a black hole is a region where our physics breaks down, where space and time lose their usual meanings, where matter is compressed to unimaginable densities. We can't observe it directly, can't visit it and return, can't fully comprehend it with our current theories, but we can study black holes from the outside, measuring their properties, testing our theories, and slowly piecing together a more complete picture. Every black hole is a natural experiment in extreme physics, showing us what happens when gravity becomes the dominant force, when space-time itself is pushed to its limits. They're testaments to the power and beauty of Einstein's general relativity, which predicted their existence decades before we had any observational evidence. They're also signposts pointing toward a deeper theory, a theory of quantum gravity that will finally unite our understanding of the very large and the very small. The journey to understand black holes has taken us from Einstein's equations through Hawking's radiation to gravitational waves and beyond. It's involved some of the greatest physicists of the past century, wrestling with deep questions about the nature of reality, and it's far from over. Black holes still hold mysteries, still challenge our understanding, still inspire wonder and curiosity. They're among the most extreme, bizarre, and fascinating objects in the entire cosmos. Places where physics as we know it reaches its limits, where the impossible becomes real, where the fabric of space-time itself is torn and reshaped. And inside each one, hidden behind the event horizon, inaccessible to observation, lies perhaps the deepest mystery in all of physics. The singularity, where all our equations fail, where all our intuitions break down, where something happens that we don't yet have the knowledge to describe. That's what's inside a black hole. A mystery wrapped in an event horizon, challenging us to understand, beckoning us toward a deeper knowledge of the universe we inhabit. Thanks for journeying with me into the heart of these cosmic mysteries. Black holes may be the universe's ultimate secrets, but every step we take toward understanding them brings us closer to understanding the fundamental nature of reality itself. And that's a journey worth taking, even if we can never quite reach the final destination. Before we end, let's take a moment to appreciate just how far we've come in understanding black holes and how much that understanding has changed our view of the cosmos. A century ago, black holes were barely even theoretical curiosities. Einstein's general relativity had just been published, and the solutions that predicted black holes seemed too bizarre to represent anything real. Even Einstein himself didn't believe black holes could actually exist in nature. He thought some physical process would prevent their formation. When Schwarzschild found the solution describing a black hole just months after general relativity was published, it was viewed as a mathematical oddity, not a prediction about real objects. The idea that a star could collapse to infinite density seemed absurd. The phrase black hole wasn't even coined until 1967 by John Wheeler. Before that, they were called frozen stars, or collapsed stars, or simply singular regions of spacetime. Wheeler's term captured the public imagination and has stuck ever since. Through the mid-20th century, astronomers slowly realized that black holes might actually exist. Subramanian Chandrasekhar calculated in the 1930s that white dwarfs have a maximum mass above which they can't remain stable. Later work by J. Robert Oppenheimer and others showed that neutron stars also have a maximum mass. Above that mass, nothing could prevent collapse. A black hole would form. But it wasn't until the 1960 seconds and 70 seconds that observational evidence started accumulating. The discovery of quasars, extremely bright objects powered by supermassive black holes, showed that something was producing enormous amounts of energy in the centers of distant galaxies. The discovery of X-ray binaries like Cygnus X1 provided evidence for stellar mass black holes. Theoretical work by Hawking, Penrose, and others developed the mathematics of black holes and proved theorems about their properties. The golden age of black hole physics was underway. Fast forward to today, and black holes are no longer speculative. They're observed objects, studied in detail, crucial to our understanding of galaxy evolution and stellar death. We've imaged their shadows, detected their mergers, measured their spins and masses. We've tested general relativity in the strong gravitational fields near event horizons and found it accurate to incredible precision. We've seen how black holes shape the universe on the largest scales, regulating star formation and influencing the structure of galaxy clusters. And we've found that black holes raise deep questions about quantum mechanics, information theory, and the nature of spacetime itself. They're bridges between different areas of physics, connecting astrophysics to particle physics, general relativity to quantum field theory, thermodynamics to quantum information. Understanding black holes requires bringing together all these different domains, and in doing so, we're pushed toward a more unified understanding of physics. This is the power of studying extreme objects. They don't just tell us about themselves, they illuminate the fundamental principles that govern all of reality. When we study black holes, we're not just learning about exotic objects in distant space. We're learning about the nature of gravity, the structure of space-time, the behavior of matter under extreme conditions. We're testing whether our most fundamental theories are correct or whether they need to be revised or replaced. And we're being humbled by the realization that there are phenomena in the universe that push beyond our current understanding. The singularity at the center of a black hole is a place where our physics fails, where we must admit that we don't know what happens. This humility is important. It reminds us that science is an ongoing process, not a completed body of knowledge. We're still discovering, still learning, still being surprised by what the universe shows us. Black holes have been full of surprises from the beginning. The prediction that they radiate and evaporate was a surprise. The discovery that information might be preserved despite falling into a singularity was a surprise. The observation that supermassive black holes correlate with galaxy properties was a surprise. The detection of gravitational waves from merging black holes was a confirmation of theoretical predictions, but the specific properties of the merging black holes held surprises about stellar evolution and black hole formation. And there will undoubtedly be more surprises to come as our observations improve and our theories develop. The universe has a way of being more interesting, more complex, and more beautiful than we imagine. Black holes embody this perfectly. They're simple in their basic properties, described by just three numbers: mass, charge, and spin. Yet they connect to the deepest questions in physics and challenge our understanding at every turn. They're the most extreme objects we know of, yet they're also common, existing by the millions in every galaxy. They're invisible, yet they shape the visible universe in profound ways. They're destroyers, consuming everything that falls into them, yet they're also creators, triggering star formation through their jets and outflows, helping to build the structures we see today. This duality, this combination of simplicity and complexity, of the mundane and the exotic, is what makes black holes endlessly fascinating. Every answer we find raises new questions. Every observation reveals new phenomena to explain. Every theoretical advance opens new avenues of research. It's a field that's alive and dynamic, where fundamental discoveries are still being made, and it's a field that connects to some of humanity's oldest questions. What is the nature of time? What happens when we die, when we're destroyed? What lies beyond the limits of our perception? These are questions that philosophers and theologians have pondered for millennia. Black holes give us a scientific context for approaching them. At the singularity, time ends or transforms into something we don't recognize. When matter falls into a black hole, it's destroyed in a physical sense, disassembled into its constituent parts, and eventually, we think, radiated away as random thermal energy. Beyond the event horizon lies a region we can never observe, never access, never fully comprehend from the outside. These aren't just abstract scientific questions. They touch on deep human concerns about existence, mortality, and the limits of knowledge. Black holes give these ancient questions a concrete physical form. They show us that the universe contains genuine mysteries, places where we must acknowledge our ignorance and accept that some things may remain forever unknowable. But they also show us the power of human reason and observation. We've never visited a black hole, never will visit one. Yet through mathematics and observation, through theoretical reasoning and careful experiments, we've learned an enormous amount about them. We've inferred their existence, measured their properties, imaged their shadows, detected their mergers. We've done this from a distance of thousands or millions or billions of light years, using tools that range from radio telescopes to gravitational wave detectors to sophisticated computer simulations. This is the triumph of science, the ability to understand phenomena far beyond direct human experience through careful observation, logical reasoning, and mathematical analysis. Black holes remind us of both the limits of knowledge and the incredible reach of human understanding when we apply our minds systematically to the study of nature. And with that, we come to the end of our exploration of what's inside a black hole. We've journeyed from the event horizon to the singularity, from the formation of black holes to their eventual evaporation, from Einstein's equations to the frontiers of quantum gravity. We've seen that black holes are real objects in the universe, common enough that millions exist in our galaxy alone, yet exotic enough that they challenge our deepest theories about physics. We've explored the bizarre phenomena that occur near black holes, from time dilation to spaghettification, from frame dragging to Hawking radiation. And we've confronted the ultimate mystery, the singularity, where space-time itself breaks down and we must admit the limits of our current understanding. What's inside a black hole? A region of space-time warped beyond recognition. A place where time and space swap roles. A path that leads inevitably to a singularity we can't fully describe. And perhaps most fundamentally, a mystery that continues to drive physics forward, pushing us toward a deeper understanding of reality itself. Black holes are the universe's way of showing us that there's still so much to discover, so much to learn, so many wonders waiting to be revealed. They're extreme objects in extreme environments, and they have extreme implications for our understanding of the cosmos. From the smallest quantum effects to the largest scales of space-time, black holes connect everything, revealing the unity underlying the apparent diversity of physical phenomena. Tonight, we've explored these connections, traced these mysteries, and stood at the edge of the knowable universe, peering into the darkness of the event horizon. What lies beyond may always remain partially hidden, but the journey to understand it is one of the great adventures of human thought. Thanks for taking this journey with me into the heart of darkness, to the edge of space-time, to the limits of physics and beyond. Black holes are more than just cosmic vacuum cleaners or exotic objects in distant space. They're windows into the fundamental nature of reality, laboratories for testing our deepest theories, and reminders that the universe is stranger, more beautiful, and more profound than we ever imagined. The space-time trap with no escape continues to hold its secrets, but every year we understand a bit more, observe a bit more clearly, and come a bit closer to comprehending these most extreme of all cosmic phenomena.